In this video, we're going to talk about how we actually compute line integrals, and then we'll do some examples. In our last video, we defined the line integral of f over a curve C be the limit as delta s goes to 0 of the sum of f of xi, yi, delta s. This Riemann sum definition of the line integral isn't very useful for us when we actually want to compute things. To compute things, we'll start by defining our curve C using parametric equations or as a vector equation. So let's say our curve C is defined by r of t equals x of t, y of t on the interval from a to b. As an aside, let's recall some of the things that we learned about vector-valued functions. First, we know that the arc length of a curve from a to b is the integral from a to b of the magnitude of r prime of t dt. Then when we talked about arc length parameterization, we were able to write s in terms of t. Using the fundamental theorem of calculus, we can find that the derivative of s with respect to t is magnitude of r prime of t. So this gives us the relation ds equals magnitude of r prime of t dt. And this gives us a way to compute line integrals. The line integral over c of f of x, y, ds is the integral. Well, we're going to replace the x and y in terms of our parameterization. So x's I'm going to write in terms of t, and y's I'm going to write in terms of t. And then the ds we can replace with magnitude of r prime of t dt. And this integral will go from a to b. So this is how we're going to compute line integrals. Let's take a look at some examples. In this first example, we're asked to find the area under the surface z equals xy on top of the line segment from 1, 2 to 3, 1. So first, we're going to need to come up with a parameterization for a curve. In this case, it's the line segment from 1, 2 to 3, 1. To define a line segment, we need to know its direction, and we need to know a point. Well, the point is easy. We can pick the point 1, 2. The direction we can calculate by taking the difference in the x-coordinates. So 3 minus 1 gives me 2, and then 1 minus 2 for the y-coordinate gives me negative 1. With these two pieces of information, we can write down our parameterization. R of t equals 1 plus 2t for the x component, and 2 minus t for the y component, where t goes between 0 and 1. Before we compute the line integral, we also need to figure out the magnitude of r prime of t. So let's first calculate r prime. We have r prime of t, that's just 2 and negative 1. So magnitude of r prime of t is square root of the x component squared, which is 2 squared, plus the y component squared. That's negative 1 squared. So we have square root of 5 here. So the line integral using our formula is integral of f of xy. In this case is x times y, but we want to write this in terms of our parameterization. So x is 1 plus 2t, y is 2 minus t, then I have magnitude of r prime, so that's times square root of 5 dt, and we're evaluating this integral from 0 to 1. To compute this integral, we need to multiply out the inside. So we have 2 and then plus 3t minus 2t squared. All of this times square root of 5 and then dt. Pulling out the square root of 5 and computing the antiderivative, we have 2t plus 3 halves t squared minus 2 thirds t cubed, evaluated from 0 to 1, which is square root of 5 times 2 plus 3 halves minus 2 thirds, which simplifies to 17 square root of 5 over 6. So that's the area under the surface z equals xy on top of the line segment from 1, 2 to 3, 1. In this next example, we want to evaluate the line integral of x squared plus y squared over some curve c, where c is the portion of the parabola y equals x squared from negative 2, 4 to 1, 1. Again, our first step is to come up with a parameterization for our curve. In this case, since our curve is given in the form y equals some function of x, the parameterization is actually pretty easy. In general, you let t be the x component of the parameterization and f of t the y component. So in our case, our curve has the parameterization t comma t squared. And our interval for t is between -2 to 1. Basically, I just look at where the x values go. It goes from -2 to 1. Again, to do the line integral, I need to find the magnitude of r prime of t. So first, let's find r prime of t. That's going to be 1 comma 2t. So its magnitude is square root of the x component squared, so that's 1 squared, plus the y component squared, which is 1 plus 4t squared. So now let's compute the line integral. The line integral of f of xy ds is the integral of x squared plus y squared, but we want to write this in terms of our parameterization. So x will now be t, so I have t squared plus, and then y is going to be t squared, and I square that quantity. All of this times magnitude of r prime, so square root of 1 plus 4t squared dt, and the integral goes from -2 to 1. Now this isn't an integral that I know how to compute, so I would use math software at this point. For example, I can plug this into Wolfram Alpha and get that the answer here is 31.773. Let's try one more example. We want to find the mass of an arc of wire that runs along the top half of the unit circle, and its density at any point is given by rho of xy equals x squared times y. If this wire had constant density, then what I can do to calculate its mass is take the density and multiply by its length. But since it has varying density, what I can do is approximate its mass by breaking up the wire into smaller pieces, and on each of those small pieces, assume that the density is constant. I can get the exact mass of the wire by taking the limit as those pieces get smaller and smaller. What I just described is a Riemann sum, and when I take the limit, I get the line integral. So in this example, all I have to do is calculate the line integral of the density function along our wire. So let's start by parameterizing our wire. Our wire is the top half of the unit circle, so I can describe that as cosine t sine t. And since I want the top half, I want my t's to go from 0 to pi. Then I need to calculate r prime. So r prime of t in this case is minus sine t cosine t. Then calculating its magnitude, I get square root of minus sine t squared plus cosine t squared. And using the trig identity, we get that this is just 1. So our line integral looks like integral over the curve c of the density function rho xy ds. That's going to be the integral from 0 to pi of x squared y. So x is cosine t, so I'm looking at cosine t squared. Y is sine t, and then times magnitude of r prime dt. To compute this integral, you can use substitution. For example, let u be cosine t, but I won't go through the details here. The answer you should get is 2/3. So that's it for this video. In our next video, we'll look at some properties of line integrals.